Good afternoon, gentlemen. We will see the structural safety and reliability and introduction, the second lecture. How do we represent this uncertainty in a new shape? Before that, something we discussed in the interval, let me elaborate on it. We have seen the material properties which have slight uncertainty associated with them. We have seen the calculation procedures where there is some little bit of uncertainty associated with it. Then the layout itself, we have seen in our last class the importance of alignment, continuity of structures, connectivity of structures, and how one can intentionally or unintentionally introduce stress concentration zones in a ship. The structure, the calculations we have done so far, the bending formula does not take into account all these factors. In fact, it assumes that material is continuous, there is no stress concentration, no abrupt change of material section or connectivity. So, this is another uncertainty which comes into calculation of stress levels in a ship. What it means is that at some places stresses could be quite different from what you have calculated. Now, let us come back to what we are talking initially. How do you represent the loads and the resistance to load? Normally, if I on a straight line, if I plot mark the load that I will be having, say here, and the resistance on the same axis, then my resistance, and if this is the origin 0, let me say, then my resistance should be to the right of this curve, right. That means if this is my resistance and this is my load, then resistance is more than load. You understand? If this is my resistance and this is my load, here in this case R is greater than load. Therefore, the vessel is safe. This is a deterministic approach. Where is resistance and where is load? Now, suppose you want to represent the variation of load with regard to time. How will you do it? How will you represent the variation of load with regard to time? One way is, if I take 1000 measurements of load as the ship operates, I go on measuring load by some means, and then I plot the load in a probabilistic manner. You are all aware of what is a histogram? Do you know what is a histogram? Yes? What about you? Let me explain. We do an experiment. We have experiments of conducted on the same issue for 1000 times, say 1000 times. I measure a particular value in the same experimental setup. Then I will get values 1000 times which will not be same, but slightly varying about a mean value. Do you understand that? Do you understand what I am saying? Suppose I am doing a resistance test. I am towing a vessel in a towing tank. I tow the same vessel in the same calm towing tank for 1000 times. I will get, for the same speed, I will get 1000 different values. They may vary from each other slightly, but they will vary all the same. Or typically you take a pack of cards and pick a card every time for 1000 times. What will you get? You will not get the same card, even though you calculated that middle, approximately from the middle I will pick. So, you will pick cards which are not having the same value. Am I clear? So, what will happen? If I write the number of experiment number 0, 1, 2 like that up to 1000, and I write the result, how will the result show? It will show some value x plus delta, this may repeat itself x, this may be x plus 2 delta, this may be x plus 3 delta, this may be x plus delta, this may be x, this may be x plus 5 delta. Some such thing I will get, varying about or minus, it does not matter, x is my minimum value. That is basically the result of the experiment will vary within a certain range. How do I represent this? Another example is marks obtained in a class of 1000 students. You take the 1000 students, the marks obtained will vary. How do I represent this? Marks obtained is a better example, you can understand it very well. Suppose there are 1000 students taking the same class, same examination, there will be 1000 people, nobody will normally repeat the other fellow's mark, but if it is 100, if it is within 100 and everybody gets a integer value as mark, then you will find that people between 50 to 60 are large number, people between 0 to 10 are very small number, and people between 90 to 100 very small number. Can you understand that? So, now if I make groups of marks of 10, 0 to 10, 11 to 20, 21 to 30 like that, and plot it, then what will I get? I will have marks obtained this side and this side number of students. What will I get? Between 50 to 60 I will have large number here, maybe something like 50 or 60 students will get this, and I will get from 0 to 10 a very small number, maybe 1 student or something, 1 or 2 students. Similarly, with 100 I will get 1 or 2 students, maybe 2, 90 to 100, right, and the other things will vary between them, they will vary like this, maybe something like this. This sort of representation is called a histogram. This gives us a very good probabilistic distribution of marks in that 100 sample or that 1000 sample. What I say, if I draw a smooth curve, it will be a curve like this. Can you see that? This, if I did not have these groups of 10 marks, but I thought the marks varied continuously and the number of students also varied continuously, then I can drop a continuous graph like this. What is this called? It is called a probability density curve. How do I plot this? Number of students divided by total number of students. Okay. So, if I sum this up, the area under this will be 1. This is a basic probability theory. I suppose most of you should be aware of it, that I can draw, if I take a sample, 1000 samples, a very large number of samples, I can, and I know how that sample behaves, each sample behaves, and the behavior I can represent in the form of a probability density function. Yes? So, now I have got the same thing I can do here. The load, I take, by some means I calculate the load at so many instants of time for one ship. What do I get if I plot it? All these various loads we have discussed, they may or may not appear. Sometimes they may appear, sometimes they may not appear. Sometimes the wind speed may be 3, sometimes the wind speed may be 10. Sometimes sea may be calm, sometimes it may be rippling, sometimes it may be rough. Sometimes there may be sloshing, sometimes there may not be sloshing. So, if I take a very large number of samples of load and try to represent it in a probabilistic manner, what will I get? I will get a load curve which will look like this. Inverted bell. Okay. That is, if this is my direction of load, magnitude of load, I will have a mean value. Maybe this value is the one that is given by classification societies, that is static bending moment superimposed by a hypothetical wave bending moment. We are not sure of that, but it could be. And the loads will be less than that in large number of cases and also more than that in large number of cases. This distribution is called a probability density, the function, this function of this curve, function of the curve is called the probability density function. This has got some very peculiar properties or very interesting properties, let me say. The area under it is 1. That means, if I want to know what is the probability that the load will be less than this value, let us say it is 1, that means it will always be less than this value, because I have taken beyond the maximum value. But suppose I say what is the probability that load will be less than this value? What is the probability? What does an ordinate here represent? Coming from histogram, if you look at this curve, a ordinate at any particular point represents what is the probability that this load will occur. Suppose this value is 0.1, then I will say probability of this load occurring is 0.1 or 1 in 10 measurements. If I took total 10 measurements, most likely 1 will be this value. But this value is very difficult. Normally it is considered as a value within this range, a small range around it. Am I clear? Now, what about the probability of a load occurring less than this value? Less than this value. That means all these together. That means this area. The area of this curve will give me the probability of a load anywhere less than this value. Is that clear? Therefore, when I take this, it will be the entire area, that is 1. You get it? Now, if I want to know what is the variance of this function, then I have to square the values at various places and add them, and the total added value into, from the histogram it is easier to explain, each value squared multiplied with number of samples added up divided by total number of samples will give the mean square value of this. This mean square value, if I take the square root, then that is called standard deviation. Okay. So, this curve has this property of mean. Mean is the average mean of this. If it is symmetrical on both sides, then the mean is the center line. And standard deviation, standard deviation is the square root of average mean, average root mean square. Standard deviation is the root mean square value. Okay. Right. What does standard deviation indicate? That is very important for us to understand what is the meaning of standard deviation. Now, you look at this curve, the area under this is 1. I can have this area 1 also by another curve. This is also 1. I remove some area here and add it here. Similarly, I can have a curve like this, which will also be 1, right. Now, these 3 curves, which will have a larger standard deviation? The wider one, the last one, right. Everybody agrees? So, what is the standard deviation giving me? It is giving me the spread of the curve. Do you understand? What is the difference between these 3 curves in the physical sense? If I have got a mean, same mean, I take the mean as same in 3 cases. One case standard deviation is small. That means the curve is peaked. This is peaked. That means large number of samples will have a value near the mean. I can say nearly 80% of values will be near the mean, right. But as the standard deviation increases, you can see in the last curve, you can't say what is likely to the value. Will it be near mean? No, it can be quite far from the mean, a large number of values. You understand this? So, now when you are talking of the load, it would normally take a bell shaped curve like this with a reasonably good spread. It will take a reasonably good spread. Do you understand? Right. How will my resistance curve appear? This is my load curve. How is my resistance curve? My resistance curve, though I have listed a number of variables, normally the property of steel is fairly constant. I have taken good care in my design. I have not left some spaces which are unconnected or alignment is improper or things like that. So, my resistance curve will be towards a peaked curve. That is what I would like to expect. Am I clear? So, if I draw a peaked curve, the resistance curve, also understand that you cannot design a ship for any eventuality. So, if I draw my resistance curve, if my resistance curve was here, if this was my resistance curve and this is my load curve, then my resistance is completely to the right of the load curve. My vessel is absolutely safe. But this is normally not the case. Why? Because if I want to have a peaked resistance curve completely to the right of the worst case of load, then my weight of my structure will go up tremendously. And always any engineering device is a compromise between cost and technical value of the product. So, I cannot go here. Normally, I will go for a structure which will be peaked something like this. Do you get it? That means the mean of the load curve is to the left of mean of the resistance curve. This is the actual, this is the ideal case. We do not discuss this. Let us look at this. So, this is normally our design practice. This gives us some very interesting information. that there is a little bit of area here where resistance is less than load. You can mathematically define it as the area of failure. This is the place where the structure will fail. If the load increases and the resistance of the structure also unfortunately on the left, the vessel is likely to fail. Isn't it? Now, in classical analysis, we consider the mean load and mean resistance, the so-called safety factor approach. Okay, so this measure, this area gives a measure of reliability of ship structure. In fact, this is the failure area. So 1 minus the failure area is the reliability of the structure. You understand? So this gives us a measure of reliability of the structure. Why don't you do it then? We haven't been able to implement this calculation into ship calculations so far because of getting the nature of these curves. We don't know. As you have seen, it depends on so many factors that it's difficult to model these curves. That's one. Anyway, let's complete what we are talking about. So, if you want to design a structure on reliability principles, then you have 3 levels: reliability based, structural design. You have level 1, level 2 and level 3. I will just introduce this to you and not go into details. Level 1 is the one that is used in shipbuilding. It's called the safety factor approach. Where safety factor S is equal to, what is it? Ultimate or yield strength, depending on who is doing the calculation. Isn't it? So this is the safety factor approach which we normally use in standard structural design, including ships. All classification societies have a safety factor for all their formulations varying between 1 to 5. But this approach takes 2 values, one value of load, one value of resistance. It does not take this into account at all. Level 3 on the other hand is a more theoretical approach where we model these curves exactly, and if they can be mathematically modeled, it is possible to find the area enclosed between the intersected portion, and that becomes our failure area, and based on that we can say that this structure which is likely to experience this load and which is likely to have a resistance of this nature will have a reliability index so much, which will be 1 minus the failure index. But this is very difficult. The level 3 reliability is extremely difficult, mainly because we do not know the nature of these curves. Even if we know the nature of the mid portion of the curve, we do not know the nature of the ends of the curve. which is where you are actually doing the integration to find out the failure mode. So, that is why level 3 is extremely difficult, and we have not come up to a stage in ship structures to apply this to design. That is when we can give the design, our structural design, a reliability index. That stage has not come. I can say my reliability index is 0.9 or 0.8 or something like that based on these principles. That stage has not come. However, in offshore structure design and aircraft design, level 3 based calculations of structural design have been implemented. Where we are in ships is somewhat in between level 1 and level 3. It is a semi empirical method with certain assumptions and certain formulations of these curve shapes. It is called level 2. Even that has not been implemented into codes. We are still, our entire structural design in ships is still based on level 1 analysis. Am I clear? Okay, now there is a very interesting thing I want to bring to your notice. This is for a new ship. What happens for an old ship? As the ship becomes old, what happens? Yeah, tell me what happens.
Curve will move more heavy.
R will start moving left.
So R will
Right.
greater
R will move left, and also R will have a better, more spread. So, this curve will change itself to something like this. In fact, it will not come much this side. This curve will be shaped something like this. It cannot increase resistance. So, it will be skewed. Depending on how old you are, either how old is your ship and how you have maintained it, this curve will either become like this, or it may even become like this. Remember, the area under this is still 1, each individual curve. My scaling is not proper. So, what do you see here? The reliability of structure is drastically falling as the ship becomes older. I intend to talk to you about the resistance characteristics of an old ship now for the next 30 minutes. What happens in an old ship? Why is an old ship? What we have seen so far is structurally an old ship is more unsafe than a new ship. What is it that has happened with the old ship? Let us see what has happened with the old ship. It is corroded, paint has fallen off, it has corroded. Corrosion could have been general corrosion or pitting corrosion. That is all. Anything else?
Fatigue.
Yes, some fatigue might have taken place. Sorry? Aging of steel, yes, fatigue. Okay. Correct. Very true.
modifications carried out, so repair works, modifications carried out.
Yeah. What does it do? It brings back the strength. Huh?
It changes the uniformity of the material which is there. Some patchwork is there, so
Well, okay. Okay, let us see. I will start with some measurements, some analysis we have done ourselves. We have taken a lot of ships and taken the thickness gauging, which all classification society demand that it be done. And normally classification societies require a change of plate or section if 25% thickness reduction has been done at any place. Am I right? Yeah. 20%. Okay. 20%. Now, we have taken a large number of, we have actually taken some standard thickness gauging books and analyzed some thicknesses. Very interesting results we have found. I will first list them to you, then we will discuss why so. In the entire ship bulk carrier, we found that the lower stools of transverse bulkheads corrode more than the bottom plates. In fact, they corrode the maximum. Lower stools of the bulkheads of a bulk carrier. Why that is so, we do not know, but there is a maximum corrosion taking place there. But the ships had different quality of paint. For the same age group, we found that the painting has a very large effect on corrosion. Why is that? Can anybody tell me? Painting, why should it have a large effect on corrosion? Because of two or three things. One is the paint quality. How good is the paint? Can it withstand the time for the next maintenance, or it peels off in the middle? The other and most important thing is how it is applied. Paint has a shelf life, how it is stored, and how it is applied. We know very well that a paint, if it is applied in moist condition, it generates bubbles inside the paint, and therefore it may generate air holes which may crack and cause corrosion. But all shipyards, wherever you are painting, is in moist condition. So how do you do? Normally the paint manufacturer suggests a painting procedure. Through his R&D effort for his paint's best use, he suggests the painting procedure, a speed of painting, whether it is spray painting or manual, if so, how many people have to work, if it is spray painting, over what duration of period the entire one coat of paint should be applied, so on and so forth. Shipyard may or may not have its own workers, may have contractors, people doing the painting, but do the painters that do the paint work, have they been properly briefed about the method of painting, that they can do the painting properly? These are some of the things that determine how effective will be the paint. Also remember that the vessel flexes when at sea, it hogs and sags. Now that curing of the paint therefore is very important. If uncured paint or paint given in varying thickness would perhaps generate stresses in the paint itself, and it may not be able to withstand, so it may flake. When it does that, wherever there is a little gap, invisible gap perhaps, corrosion starts immediately. Corrosion. Okay, let us see what other things. We have found that different ships painted with different quality of paint as well as different places have an effect of corrosion. Another important thing we found is that ships up to about 10 years of age corroded less than ships beyond 10 years of age. This is interesting because every ship goes for a major survey at 5 years, and after 5 years the entire paint is removed and new paint is given, and the plates that have corroded till that time they are replaced. So after 5 years or after special survey, ship is as good as new. Why does it that up to 2 surveys the ship corrodes less and after that it corrodes more? Maybe some things you people have said, will have some effect, that the ship has undergone maintenance procedure, and during the maintenance we do not know how much care has been taken, whether some built up stresses have been developed, whether continuity of material has been broken, whether connectivity has been compromised, whether due to bad welding procedures stresses have been developed, that is stress concentration has taken place and locked up stresses are there in the structure. But still this does not generally tell us why almost all cases a ship beyond 10 years has corroded more than a ship less than 10 years. There must be something more, corrosion. Perhaps we do not understand fully about corrosion. Okay. So, that is one observation we have made. I thought I will share it with you. Generally, when you observe the uh, thickness diminution over a large number of ships, you can group all the ships into three categories: good, average or bad. Good ships are one which have relatively good paint quality even after 5 years, corrosion is less, maintenance work required is less. Generally new ships come under this category because while taking delivery of the ship, owner makes sure that all the contractual obligations are met regarding painting by the builder. So, the ship is in good condition. An average ship is one which has perhaps been maintained well, and therefore, the thickness reduction is controlled, and it could be the older ships even beyond 10 years. But the bad ships are definitely beyond 10 years, and perhaps they also have not been maintained well. So, the corrosion is large. Another interesting thing we found, that the new ships, that 10 years before ships, if you draw a probability density curve of thickness diminution, you will get something called a gamma distribution, like this. That means thickness reduction is maximum towards the left hand side, and large thickness reduction is small. Whereas, when you go towards older ships, the curve changes to a normal distribution, that is thickness diminution is more over large area, large thickness diminution is there. You understand? Some of these points led us to look at corrosion and corrosion related stresses or stress related corrosion. So, we have looked at corrosion. If there is an area which is open, the metal surface is open, it may corrode. Would it be right to say it may corrode, or would it be right to say that it will corrode? It will corrode. I would still like to say it may corrode, because corrosion is basically a electrochemical activity, and that takes place because two dissimilar metals must be present for corrosion to take place. It cannot take place with single metal. How does it take place at sea? How does it take place in the case of a ship? Ship is all made of steel. So, this galvanic action can take place with very minute degrees, that is residual metals, also in the material itself or in the sea or in the form of barnacles on the sea surface, whatever it is. So, we can understand from here that corrosion can take place anywhere in the right environment, that is moist climate where oxygen is available, and one metal will degrade and the other metal it will be deposited. So, normally all plates corrode. So, suppose we know a particular place where corrosion is taking place in an average manner, we call that general corrosion. This is also affected by the temperature. So, if you have got a cold temperature or a hot temperature zone inside the ship, the corrosion rates will vary. The dissimilar metal presence in water or in the metal itself will vary from place to place. We also know certain other properties, that is, if the water is flowing past the metal, then corrosion rate is slower than if the water is stagnant. That is, a vessel standing still in a port will corrode much more than if the vessel is moving. Correct me if I am wrong in all these observations. So, when a ship is standing at port, it is likely to corrode more. When it is moving, it is likely to corrode less. It is very difficult to draw up a mathematical relationship between the fluid velocity and the rate of corrosion, particularly in case of ships where there is a big thick boundary layer growing around the ship as you go towards the stern. We have to stop corrosion, we have painting, we have artificial anodes, sacrificial anodes, etc. But then all these things must be done with care. Typically, we have discussed about painting. I would also mention to you about cathodic sacrificial anodes. The distribution of sacrificial anodes in a particular area must be well designed, so that all the anodes give way or get sacrificed in a uniform manner. If certain anodes are get eaten away faster than the other anodes, at the end you will have a corroded place somewhere else. So, this is also another area which must be looked at carefully. Okay. So, we understand something about corrosion. What I have been trying to tell you is that corrosion behavior around a ship is typical to the ship itself. It is not that if a sister ship moving in the same route will corrode in the same way. It is not like that. That is, if I have a ship corroding in a particular manner, then another ship going in the same route may corrode in a completely different manner. Therefore, it is told that corrosion is more like a fingerprint of a ship. That means it identifies the ship, but that requires a lot of effort. You have to have a corrosion history to know the behavior of the ship vis-a-vis corrosion properties. The other thing is stress concentration. We have talked about stress concentration. We know that during the life of the ship, during maintenance period, stress concentration may increase. We know that. Now, a plate has corroded. Generally, you will understand, you can also do this exercise if you wish. I got a ship section here. I have calculated the section modulus, and you can assume that the deck plating and the keel plating have reduced by 25% thickness at the end of a 5-year cycle. Just assume that the top plating and the bottom plating farthest from the neutral axis have reduced in thickness by 25%. What is the increase in stress level? What will happen if these thicknesses reduce? If you have done a I by Y calculation, a section modulus calculation, then you will know that section modulus contribution of this and this is the highest, isn't it? So, if 25% is reduced here, you will have nearly 10% reduction in section modulus. You can do this, you can calculate and find out. So, first of all, when corrosion takes place, maybe towards the end of the survey period, you have a high stress value on deck. If on top of that there was some stress concentration at a particular place, then you are in trouble, a crack may develop. So, this two effects, when they are added together, that is, a corrosive plate has reduced strength, plus if there is additional stress due to stress concentration. These two effects can be added, numerically added, but perhaps the total effect is more than the harmful effect, is more than if you just look at the stress levels. That is, a stressed corrosive plate is more probable for damage than if you consider the stress alone and corrosion alone and added the two. This phenomenon is called stress corrosion cracking. Plate cracks due to stress and corrosion. This is one which you have to be very careful about. See, we have seen the uncertainties in material properties. Now, you see how severe it can become. Corroded plate can give you a 10% reduction in section modulus, but if also you have stress there, additional stress because of some locked up stresses due to welding, bad welding, you are putting doubler plates arbitrarily to solve a temporary problem, you are actually aggravating a bad situation. Then the other thing is fatigue. All of you have talked about fatigue, so I need not spend much time on fatigue. It seems you know everything. Okay, you know what is a SN diagram? Yes? Okay. So, a SN diagram will look like this, right? Yes or no? This is what? This? Okay. What does this diagram tell us? It tells us that at low stress levels, sorry, low cycles, more stress can be withstood, right? That is, in other words, if I have a high stressed region, then that region will withstand less number of cyclic load. If it increases, then it will fail. Whereas, if the stress level is low, then it can stand much more number of cycles. What happens in case of ships? We are talking low cycle or high cycle? Normally, for the main ship structure, we should be considering descent. Stress levels are high. So, it will normally withstand low cycles. Therefore, normally it has been found for a average ship which does not have much of variations in loading patterns. A 20-year life cycle is good enough for the normal metal to withstand fatigue. But again, one is not sure. If, for example, you alternate between full load and ballast, or hogging and sagging condition due to operating conditions, then the cycle pattern, stress change cycle pattern changes. Typical example is your ballast water management system, the solution that was given earlier, that you have a sequential deballasting of tanks and filling. That would lead to alternate stressing as you deballast and ballast. So, that would increase stress. Very interestingly, another thing you can observe, if I have a high strength material where it can have a high stress value, then normally one would think that fatigue will increase, the fatigue strength will increase. Okay. Suppose steel was here, I can go for another material which can go to the left, and the fatigue strength will increase, provided of course I maintain within that cycle. But some general observations regarding fatigue indicate that it is not so. That is, when something is some metal is fatigued, it tends to strain, that is, it elongates. Once it elongates, this curve is no more valid and is likely to fail. It goes beyond elastic limit. It is actually related to amount of strain the material is going through. So, when you use high tensile steel or high strength material, we normally go for more stress levels, more elongations, thinner material, therefore, again more elongation, and therefore, we compromise with fatigue strength. So, anyway, we can draw some conclusions regarding fatigue limit. I have just told you one regarding higher strength materials which may indicate higher stress values for fatigue, but since the material used is of low thickness, there may be higher strain and this fatigue limit may be much less than normal shipbuilding quality steel. Surface finish is very important for fatigue. If the surface finish is good, that is related to shot blasting and painting. If that is good, your fatigue conditions are good. Otherwise, fatigue can set in very quickly. Stress concentration areas, if they are subject to cyclic loading, then fatigue strength reduces drastically. Therefore, that is another important point. Corrosion. Corrosion fatigue is something we still do not understand very well. We think that a corroded plate fatigues very quickly. It is by observation only. There is no scientific data to support this. Work is going on. Lap welds lead to discontinuity of material. So, if you are designing something for fatigue strength, then we have to go for butt welds. So, these are some of the reasons for which we believe old ships are more prone to failure than new ships, and they keep changing, going towards the left side of the load resistance diagram. The resistance keep going to the left, and the orientation of the curve, whether it should be oriented towards right or left, depends on mainly your maintenance scheduling and how well you do maintenance. Thank you.